Yeah, you can go ahead. Hello? Diganta.
Can you give me permission to share screen? I think I don't have a screen sharing permissions yet.
Okay. Yeah, you should have now. Sorry. I should come here 10 minutes earlier to have everything set up. Okay. You must, yeah, you should have.
Yeah, so is my screen visible?
Yes.
Okay,
You should
okay.
go to full screen.
Yeah, I'll go to full screen. Yeah. Okay. So yeah. Right. So this is basically just going to be a very high level view of what neural networks are, mainly for people who may or may not have seen what neural networks are before. And I'll talk a little bit about why we would want to use something like a neural network in the context of machine learning. And um, when we move on to verifying neural networks, what is it about neural network that makes it a little bit hard to verify, right? So in general, there's machine learning is going to talk about a lot of problems which are in some sense difficult to even pose as questions for a standard algorithm, right? So for example, if we are looking to take an image from a camera, and then image is just some array of pixel values, and we're saying that we're going to identify whether an image is a cat, right? How would you write a standard algorithm to do that? There is really no good way of doing it, right? Because we don't even know what a cat is, right? We don't have a nice mathematical definition of what a cat is, which is going to make writing some sort of a standard algorithm to do that very difficult, right? But yet, it's not a very hard problem for a human to do, right? If I show you a picture and ask you whether there's a cat in that picture, it's fairly easy for you to tell me whether or not the cat is there in the picture or not, right? So how? Yeah. Hello.
No, go ahead.
No, okay, sorry. Yeah. So how do we as humans actually solve these problems? How do we, given a cat, identify, given a picture, identify whether or not there is a cat in it, right? So if you think about what a human sort of, when they slowly, you have a baby and they slowly learn how to identify a cat, really what they're doing is they're looking at huge number of examples. So every day they might be looking at a picture of a cat or looking at some book and saying, okay, this is a cat, right? And then the mother or father will slowly teach the child, and eventually after seeing a lot of examples, we get some kind of an idea. As humans, we get some kind of an idea of what a cat is, and we learn to identify them, right? So this is sort of the idea in general behind machine learning, where the idea is that we have examples as opposed to clear algorithms, right? We don't know what a cat is, but we have a bunch of examples of images of cats, right? I can easily go online and download some 10,000, 100,000 examples of images of a cat, right? And I can also download some 10 or 100,000 examples of images which don't contain a cat, right? So we have such examples and large number of such examples, but we don't have some clear algorithm of identifying. Can we sort of learn how to identify a cat, or learn the algorithm given these examples, right? And this is in general what sort of machine learning aims to do, right? So these examples could be data. In general, data can be labeled or unlabeled, right? So what do you mean by that? I mean that the data can be, labeled data is usually some input or output pairs. Like, for example, here's an image, which is the input, and here's the output, which is whether or not the image contains a cat or not, right? Or you can have unlabeled data, right? So unlabeled data can be just raw data. So here is a bunch of different text documents, and just tell me which of them are close to one another, right? Or here's a long passage, and tell me which kind of words appear in the context of other words, and so on, right? So in general, you have a lot of these data, and in machine learning, we would take this data and somehow train or learn on these data. And at the end, what we get is we get a function, right? So for example, continuing our running example for this cat identification system, we have this some 100,000 images, and for each image we know we have some label that either this image has a cat or not doesn't have a cat, right? So maybe these 100,000 images we have just generated by doing something manually or downloading from the internet, right? But now once we have trained our system or machine learning system, in our case it will be a neural network, on these images, what we get at the end is a function. This function is going to sort of have the desired behavior, which in our case is that you can feed the image to the function, and that function is going to tell you whether or not the image actually contains a cat or not, right? The idea with machine learning is that this training process is going to be general, right? So it will work not just for cats, but also for dogs. It's not like we're somehow exploiting some special feature of an image which will tell us whether or not it has a cat or not, right? It's not like we're exploiting some special feature of a cat itself, right? This will work for a dog, this will work for a chair, this will work for a car, right? So it's in general, this is fairly widely applicable. The same sort of framework, same sort of methods will give you a neural network that once you've trained it can learn to identify any different kinds of things, right? So this in general is what we mean by when we say machine learning is general, and it can be even other tasks, not just image identification, right? So it can be, instead of images, you can have some other kinds of data. You can have some text, and you might say that the output is, okay, what is the mood of the text? Is it a text that is positive or negative in terms of sentiment, right? So you can have words, and your output can be some sort of encoding of whether two words have close meaning or are far in meaning, and so on, right? And the second sort of aspect that I want to focus on as we go into more slides is that what it turns out, at least a large part of modern machine learning tends to be mostly black box. What do you mean by that? What I mean is both the training process and the function that you get at the end of the day, it's not very clear. Even if I were to give you the function, you can see that, okay, some 99% of the time, if you give it an input image of a cat, it answers correctly, right? But it is not very clear why or how it does that. So it is going to be some fairly complicated function, and what each internal part is doing, while we have some intuition for it, it's not very easy to understand what is it exactly that is happening internally inside the function, so that it is able to identify a cat, right? So which makes it very difficult to understand what is going wrong when things do go wrong. Like if I give it, if this function suddenly is misclassifying certain images, it's often hard to understand why. This is, given that this is the general sort of framework of machine learning, this will sort of motivate us to understand what a neural network is in a more general sense, right? So in very generally, this sort of framework of machine learning would require us to learn some sort of a function, right? Now, this function in general is usually given by in this sort of a parameterized form, right? So instead of, so generally, if you want to learn a function, it's kind of a problem where you have to sort of fix a sort of a space of function that you're going to look at, right? So you have to look at some class of functions, and you have to select one of them, right? So in machine learning algorithms, usually the way people do is they set up something they call the parameterized function approximators, right? So when I'm saying that machine learning algorithm is going to learn a function, and what I'm really saying is it's going to learn this parameters function approximator, right? Or one sort of value of the parameters for a parameters function approximator, right? So what is a parameters function approximator? So it's some function that is going to take x to y, but the behavior of the function is given by a value of some other parameters, which are also just some real values, for example, like theta, right? A very sort of direct example is a linear function, right? So I can say that I have y is equal to f of x given theta m theta c. So here theta is sort of got two real values into it. So theta is a two-dimensional real vector. And then what is this function? What is this y given by? So it's given by just theta m times x plus theta c, right? So as I keep varying the values of theta, the behavior of this function changes, right? So if I'm doing, for example, if I know that, for example, I'm trying to learn a function, I know that I'm satisfied with only looking at real valued functions, then I can sort of rephrase or reduce the problem to finding the values of theta m and theta c, right? So if I found some values of theta m and theta c, I found a particularly linear function. And in turn, every possible linear function I could think of is going to be given by some pairs of values of theta m and theta c, right? A slightly more complicated example would be quadratic functions, right? So let's see what this means in the context that we're talking about before. So again, we'll have some data. So in this case, the data is going to be some x and y values. This might come from various kinds of real world situations. Maybe, it is the distance that a car takes to stop given amount of braking pressure the car provides, right? So let's say that this is my input values x, and I'm sorry if this is slightly hard to read. So I usually use this pen, but this has stopped working for some reason. So yes, and this data is going to be just a bunch of points, right? So maybe you have some points like this, right? And so on. So now what we're doing in machine learning is we're going to slowly somehow optimize our functions, or we're going to slowly somehow find more and more functions or more values of theta, so that somehow these points are being closely matched, right? So we're going to try and find some values of theta 0, theta 1, and theta 2, so that what we get is essentially a parabola of this shape. And if we can find that, so if we can find values of theta 0, theta 1, and theta 2, so that this parabola actually matches the data very well, then what we have found is we have sort of fit our function or learned a function that, given this input and output data, it mimics the behavior that the data sort of represents very well, right? So in that point, we say that, okay, we have done training this, and we have a function that actually captures what we're trying to do, right? And this is basically what we would do in machine learning, although at a much sort of larger scale and with much more complicated function parameters function approximators, right? Yeah. So any questions so far, given this sort of a framework? So the idea is that in machine learning, we're looking for these functions. We're somehow going to find the functions, and the way that we or the framework that we operate in is that these functions are basically parameterized, and for various different values of parameters, we'll get sort of different behaviors for each one of these functions, right? So any questions or comments, doubts, anything so far?
Any questions? Yeah, the question is, if you can always find a function that fits a given set of data points, okay?
Yeah.
Data points.
Right. So this is something that I'll actually come to in some in a later slide. But just to briefly say that it really depends on the class of function you're looking for. So obviously, if I restrict myself to something like a linear function, it's not going to be possible, right? So I can have a very complicated set of data points for which there is no way, like it's no way going to be possible for me to find a linear function that fits it very well, right? But maybe if you allow for a quadratic thing, it would fit it very well, right? So, for example, one answer to your question is, in general, if you look at polynomial functions, it's in general possible to find such a function always that fits your points exactly, right? So it depends on the class of functions. And yeah, in fact, will be one of the things that motivates, one of the ways you can motivate the choice for a neural network, which is that it is a class of functions for which such a property holds. Does that answer the question?
Yeah, of course. It won't perfectly fit. Okay,
yeah.
There'll always be some, some errors in the thing, and I guess the optimization is to try and reduce that.
Right. Yeah, exactly. And there is actually very so I'll come to the theorem which basically talks about this in some detail. So yeah, I mean, in fact, you can pose this question in a particular way and get certain kinds of results out of it. So I'll come to this in more details in later slides.
Okay, go ahead. Yeah, there was another question. Yeah. Yeah, I guess you will get. I mean, the question is, you started with, the cat, and now you're representing the function as manipulating real numbers. So the
Yeah, yeah.
question, what has cat got to do with the real number?
Yeah, that is a very, very good question. So in all of machine learning and in general, whenever I'm saying functions, the idea is that you can sort of reduce an image to a very large vector of real numbers, right? So let's just say that for now we're working with black and white images, right? So if you think about what an image is, it's and let's say somehow that we fixed, like let's say that we have fixed a resolution of say 100 by 100, right? So we have this grid of 100 pixels, right? And then what you can do is you can sort of fix an order. So maybe you fix an order where you take this pixel first, then this pixel, and so on, and then you go into the second row and so on. So if you fix some order, then what you really have, and so suppose for each values of the pixels, it's a black and white image. So each value is going to be some amount of some percentage of black or white, right? So you can say that 1 represents fully white and 0 represents fully black, and then 0.5 is like something like gray, 0.75 is a bit more white, 0.25 is a bit more darker gray, and so on, right? So you can encode your image in this way as real values between 0 and 1. So if I have 100 cross 100 image, I can sort of take this value, then which will be a value between 0 and 1, real value between 0 and 1, and take this real value between 0 and 1, take this real value between 0 and 1, and so on, right? So if I were to do that, then what I get, so each input image in that case becomes 10,000 size vector of real values, right? So this becomes my X, and X. So whenever I've got bold things, X is so whenever I'm using bold fonts, it basically represents a vector. So this is going to be my X vector, right? So this entire collection of pixel values for the entire image. Now, then I've got some label data, right? So I for each sort of input image, I have a output corresponding to it, which is, let's say, Y, right? And I say that, okay, Y is going to be 0 if it does not contain a cat, and it is going to be 1 if it does contain a cat, right? So I can have 10,000 or 100,000 such images that I've downloaded from the internet, and I've converted them into this, via this encoding into this sort of real valued vector form. And corresponding to each one of these 100,000 images, I know that, okay, given a particular image, I know that whether it is actually a cat or not. So I've got this corresponding list of Y values, right? So this is basically going to give me this sort of a data set of X values correlated with Y values. And that is basically what this function is going to train on. Of course, I can't draw a situation or a graph showing you, okay, what are these data points going to look like for a 10,000 size input vector, but conceptually you can imagine that there will be something like that, right? So from a conceptual point of view, whatever is happening there is not really any different from whatever I've drawn here. It's just that this X would, instead of being one dimension, it's some 10,000 dimensions, and this Y is, in that case, Y is still one dimension. But again, even Y can in general be larger, right? Yeah, so there are these encodings by which we can sort of reduce things down to these real valued numbers to real valued numbers sort of thing. Yeah. Does it answer your question?
Yeah, one more point that maybe add is, because Y is also the classifier here is the discrete set of things. Okay, cat, dog, or whatever, But what the function will return will also be a real number. In general, it can be a real number. So then my question is, how would you interpret that? If there are 10 pictures, cat, dog, or something, but yet Y is real numbers, the output is the real number, then it'll be, I presume it'll be more like, how close it is to that.
Yes.
10, correct? So there'll be some fuzziness even there in the output in the classifier, okay? So that you could say then it is some kind of a probability that it is that particular classifier.
Yes, precisely, yes. Yeah. So the way you can sort of interpret the continuous output, even though really we're looking for discrete things, is precisely as Sir was saying, by this sort of a probability lens, like that. You can say that, okay, I really want a function that takes in an input image and gives me the probability of that image containing a cat or not, right? And now then I have a bunch of examples for which I know whether there is a cat or not. So I can label the probability, the output probability, as being 1 or 0. But in general, of course, then my neural network or whatever function that I'm learning is allowed to say that given an input image, I really don't know. I'm going to say it's got 50-50 probability, right? So it can output 0.5 if it gets confused, for example. So any further questions or anything here, or should I move on?
Yeah, I think you can move on.
Yeah. Okay. Right. So yeah. So now the question is, of course, we looked at these linear functions, we looked at these quadratic functions, right? So what are neural networks really? Neural networks is just one of these kinds of ways of doing a parametric function approximately, right? So basically, deep neural networks is just a fairly nice way of doing this parametric function approximation, and it's a way that works really well in sort of real life, right? So what is this? What is a deep neural network? So it is basically a structure that have a structure like this shown on the right hand side, where you have multiple layers of these nodes, which are often called neurons, right? And we assume again, like I said, that the inputs and outputs are going to be vectors of real values, right? So this first layer is where we feed the input in, right? So this is the input layer, and then somehow it passes through each one of these multiple layers, which are often called hidden layers, and the final output comes out of the output layer, right? So what happens in each sort of what happens as the values sort of pass through the layer is that each one of these edges along that are connecting one node to another, each one of them will have some weight associated to it, right? So maybe this edge has got some weight W, right? And then whatever value that is being inputted in this input node will get multiplied by W and added to the input value of this node, right? So this node's input, you can see that there's two edges inputting into this node, right? So this node's input is then going to be some weight multiplied by the value coming from this node. So you guys can see my cursor, right?
Yes.
Yeah, okay. So some weight coming from the value of this node into some weight that is along this edge multiplied by the value from this node, right? So it is going to basically get this sort of a linear combination of the values of this node and this node. So this is basically the input that comes into this particular node, and then some bias gets added, right? So if you think about what the so if I call this guy as x naught, or let's call this guy as input 0 and input 1, right? So what we're ending up seeing is some linear combination of input 0 and input 1 plus some bias that gets added. So the bias is just going to be some constant term that is going to get added, and that is the input to this particular node, right? So each node, each edge has got these labels, which are the weights, and each node is labeled by the bias. And so the input to each node or each neuron is going to be this linear combination according to the values on the edges, plus whatever the bias is, right? So then this is the input to this neuron. What is the output? So the output is basically given by applying some nonlinear activation function to this particular value of this neuron, right? So for example, you can take something like sigmoid, right? Which is a very fairly common example. So if you take sigmoid, then so sigmoid function is looks something like this, right? And the idea is that for very large values, you'll just slowly saturate to 1, and for very small values, you'll just slowly go close to 0. And if you apply any such nonlinear activation function like sigmoid or anything else, then that is basically what is going to give you the output value of each neuron, right? So this happens for this particular neuron, for this particular neuron, right? So for each neuron in the hidden layer 1, this will happen, right? And this then gives you a bunch of values that are then going to act as inputs, or that are then going to pass through the edges from hidden layer 1 to the hidden layer 2, which is finally going to give us inputs for the neurons in hidden layer 2, right? So the similar sort of a thing is happening here. So we're taking the values that are coming from the output of these nodes, we're going to multiply them by these edges, and then we're going to add some bias value, and then that is going to give us the input value of these nodes. And again, we're going to apply some sigmoid and get the output values and so on, right? So this is basically what the semantics, if you will, of a neural network is. And then finally, of course, in the output layer, we are going to take these edges, multiply them by by whatever values there on the edge, add whatever the biases are, and then that basically gives us the output value at the output layer, right? So this is basically what a neural network is in terms of structure and what it does in as a function. So why do I say that this is a parameterized function approximator? Because you see all of these weights on each one of these edges, right? All of the weights on each one of the edges and all of the bias values that are basically sitting on each one of these hidden neurons, they can all be considered as the parameters of the neural network, right? So if I were to change the values of the weights, the entire behavior of the network would basically change. And similarly for the biases, right? So I can then collect all of the values of the weights and all of the values of the biases into this huge tuple that I was writing as theta, right? So then that entire sort of tuple is basically going to give me the parameters of my neural network, right? And then I can sort of, going back to a previous framework, I can sort of say that, okay, when I'm training a neural network, what I'm really looking for is the values of these parameters, which are these weights and biases, such that the neural network behaves like whatever data, input output pairs or examples I'm feeding into it, right? So does this make sense? Is there any questions?
Yeah, one question here. What's yeah. Yeah, the question is, what is, I'm kind of paraphrasing her question. So she's saying, what is the relevance of the output of all the hidden neurons at the hidden layers? Are they something like you're learning some intermediate features and then you're trying to put them together as you move along? To finally classify.
Yeah. So that is precisely the sort of the intuition behind it, right? So in fact, that is a very so that question can be answered in multiple ways. So from an intuitive perspective, that is precisely what's going on, in the sense that if you think about something like an image, the first hidden layer would classify some very local features, like say edges, corners, and things like that. And then maybe the second hidden layer is going to identify combinations of these local features. So maybe you can put together two edges to identify something like a pipe, or you can put together multiple edges and corners to identify basic shapes. And then finally, the third layer can, take look at more combinations of these features, and a few combinations of a few shapes gives you some kind of a structure. And maybe in this way, sort of a few layers down the line, you finally are able to identify very complex things like cats, right? So yeah, that is precisely the sort of intuition. And the idea is that you're if you think that there is this sort of hierarchy of features where each set of features is going to give us a way of or each level of detail is going to give us a way of describing or identifying features of a slightly higher level of detail, then that is basically what our hidden layers are going to do. And this particular thing, whether or not actual neural networks, so when we're training these neural networks, of course we don't control any of these things, right? So we don't really ask the neural network to learn low level or mid level features, or we don't even have much way of controlling or interpreting what are these features at each level that are being learned. So another sort of way of answering this question is that another way in which people are looking at this question is actually trying to understand whether or not neural networks that are deeper, that have more hidden layers, are they able to compactly represent more information? And there is some even theoretical results on that front that say that is definitely the case.
Yeah, one more question. Yeah, two more questions here. Yeah, what is the relevance of bias?
Yeah. So the idea is that you would want to, so if you don't have bias, for example, then if you pass only zeros as the input, notice that everything that is there in this first layer will only going to get to see zeros as my input to the network, right? So if you don't have a bias, then this zero in some sense becomes a very special sort of a function, right? Like if I were to, for example, go back to this to both the linear and the polynomial cases, if I were to somehow shift all of my input points by a small amount, right? Or if I go to, if I talk about the cat case, right? If I were to add a very slight value to my image, right? So like I say that, okay, for whatever reason, all of the examples that I'm training on, they have some 0. At least some 0.1, brightness to them, right? So then that is going to mean that whatever that was my previous classifier, if it somehow is even able to learn the function when everything is between 1 and 0, now that I've suddenly shifted everything to 1.1 and 0.1, if I don't allow for bias, it may not even be possible to represent those functions, right? So if you want to be able to talk in general about all kinds of functions, you would need to have some bias, right? Because otherwise all the functions that you can talk about as a neural network is going to only be centered around zero, right? It's similar to the intuition that you have as to why you would need bias in this parabola case, because if I always fix this to zero, if I don't have a bias here, I can only represent parabolas that are centered around zero, right? I can never talk about a parabola like the one that I've drawn here, assuming that this is sort of the origin, right? So to get this general expressiveness, you would definitely need a bias. And also, I mean, to look at it from another point of view, um, you would want your neural network to be something that, given data in any, like it should not really matter what the sort of mean value of the distribution of data is, right? Like if my data is between, if my encoding is between 1 and 0, it should learn that whatever that I'm wanting it to learn. The similar thing should also happen if I were to, so like this encoding that I've chosen for images is kind of arbitrary, right? I could have said, instead of 1 and 0, I could have said 1 and -1. Like I'll say 1 is white, -1 is black. Or I could have said 5 and 6, like 5 is white and 6 is black, right? So no matter what I choose, it should still be able to learn things, right? It should not be very dependent or sensitive to this encoding. And if you, I mean, it is a question as to whether or not the neural network or the training process is going to be sensitive to encoding or not. But if you don't allow for bias, you know that definitely it will be sensitive, right? So that is the sort of idea that you want it to be generally expressive, which is why you would need this bias. Does this answer the question?
Oh, okay, one more question. Yeah. Yeah, maybe this. Yeah, now I think this could be probably different. Actually, the question is, how do you? It's maybe this is a question related to maybe that. How do you train? What are the initial values for theta? Okay,
Hmm.
for the parameters. Maybe we can defer this question until you get
Yeah.
to
I'll
how
give you
exactly.
some of the details of
Yeah,
that
I
right now.
mean,
Yeah.
so yes, that is what is used. The technique that is used to optimize the optimization process derives these theta, and that how exactly it is done, that will have some strategy for taking the initialization. Am I? Yeah. So
Yeah.
that's my understanding. Is how would you answer?
Yeah. That is precisely what, and I'm going to talk about details of that just a few slides down the line. I mean, at least some details of that.
Yeah.
Yeah. So maybe I'll get into just remind me. I'll get into this question so a little bit later on, a few
Yeah.
slides
Yeah.
down the round. Yeah.
Sure. You can ask that question. So when he talks about the specific techniques for synthesizing these functions.
Yeah. So far we have only talked about what these thetas are. We have not really talked about how do we even look for the theta, right? So when I come to that part, you can like I'll answer your question at that point, because then I think I'll have it's better to go into more details at that point.
Yeah.
Yeah. So yeah, so the next slide that I have is some intuition. Like I was saying, this sort of multiple levels of detail intuition. I think I've already sort of talked about most of the content of this slide while answering some of the questions that we're getting on the previous one. By the way, are there any more questions that right now?
No, you can move on.
Yeah, sure. Yeah, so I've already sort of talked about some of the things in this slide, but basically the intuition is that each hidden layer is going to identify patterns in various levels of details, and you can have layer 1 is going to identify low level, layer 2 is going to identify the combine the lower level details to get some higher level shapes, and layer 3 is going to combine shapes to get digits. So here basically I'm looking at a very sort of classical use case for neural networks. So it's kind of, you can think of this as equivalent to being hello world for a neural network. What hello world is usually for learning a new language, right? So this is one of the first things that people tried, and to this day this is the first things that people introduce, first data sets that people introduce neural networks with, which is this MNIST digit data set, right? So this is so basically a bunch of handwritten digits that have been scanned and put into this black and white format, and all of these digits come with some labeling, right? So each one of these digits have been labeled accordingly, and then the idea is that from this, I think there are some 60,000 images. From these images, you have to train a neural network to just look at the image and identify what digit it is, right? And it is precisely the sort of intuition that somebody was mentioning is what we see that neural networks tend to learn, which is that the first layer will identify some things like edges, lines, curves, and then those will get combined into things like shapes like circles and triangles, and then those will get combined into finally the more complicated structures like digits, right? So this is the sort of idea with neural networks, and why we're choosing this sort of layer by layer structure, which is that it is kind of natural to expect that in most real life cases, whatever function. Yeah.
Yeah. No, but once again, I think you already mentioned that thing. I mean, the fact that this layer 1 happens to capture lines, curves, the layer 2 shapes, etc., is not exactly is kind of accident. No, I mean, it is not. You don't have any, like you said, you don't have any control, or can you influence the structure and the way the parameters are learned, such that it fits into this kind of scheme and idea. I mean, you did mention that you don't have any control over exactly trying to do that. So, or
Yeah.
can training method that you use influence the neural network to learn in this way?
Yeah. That is definitely the case. That it's not that it's not necessarily the case that when we are training a network that um, it will actually behave in this sort of an intuitive way that I've stated here, right? But the idea is that the reason we are even having multiple layers is to allow for this sort of a thing to happen, which is that, I mean, in general, for most real world problems, they're, a very compact way of describing a function that would solve this problem would probably have this sort of a multi-level or hierarchical structure, right? And we would like to allow such sort of a structure to be expressed in whatever parametric function approximation we're looking at, right? So if you look at, for example, if you go back to, for example, linear or polynomials or quadratics and so on, there is no hierarchical structure as such over there, right? So there it's not even possible for the parametric function approximator itself to even learn such hierarchical structures, right? Whereas the layer by layer structure here allows us to learn such a things. Whether we actually learn such a thing, or whether it's just some other complete random set of weights and biases that we get, that is a very that we don't really have any control over, and that is true, that we don't have any control over that aspect of things, right? But it is that the motivation behind having multiple layers in neural networks is that we should at least be able to express and learn such hierarchical structures. So this is something that can happen if we allow for multiple layers, and which is why we sort of have multiple layers in a neural network.
Yeah. Okay.
Yeah, this is
so that's the
yeah,
theory of this.
right. Yeah, and interestingly, there has been some recent work which has shown from a theoretical point of view that there are certain functions where you can have very small multi-layer neural networks, but if you allow for only a single layer neural network, you can't approximate that particular function unless you go for a much larger neural network. So there are sort of people are looking at some theoretical results like that as well.
There's one question. Yeah.
Yeah.
The question is, you said it was a black box, but then you decide how many layers, and there is something about the structure, and then well, the person who asked the question, he also said that you decide the theta, okay, which is not exactly the case. I'm adding this comment, okay, because the training process decides what the theta should be. Therefore, why do you, to complete his question, then why do you say it's a black box? Okay.
Yeah. So what I mean when I say that it's a black box is that it is, so I'm comparing sort of two things here. So when I'm saying that it's a black box compared to something like a program or a classical algorithm, right? If somebody were to give you a program that identifies a cat, you could probably sit and like look at it for some while, and you'll be able to understand what was the thought process behind whoever made it, and what is it that the program is actually doing, or how is it that the program is actually identifying what a cat is, right? All that I mean when I say that a neural network is a black box is that that sort of a thing is much harder, right? So if I give you, for example, a neural network that has got some 500 nodes in layer 1, 400 nodes in layer 2, and so on, right? So like, let's say it's got 5 layers. Let's say that it's got 5 layers each with 500 nodes, right? So this is going to be some complicated structure like this, and really all that you have to stare at is these values of these weights and biases. Just by looking at the values of the weights and biases to understand what is it actually that is happening in each node is a fairly difficult problem, right? Like, I mean, if I were to give you just some values of weights and biases and ask you, okay, what is it that this neural network is doing, right? What has this neural network been trained to do? You can, I mean, even if you tell you that it's an image, and then ask, okay, what kind of objects that is this neural network identifying? I'm telling you that it's identifying something. What kind of objects is it that it's identifying, right? You can imagine that is going to be a fairly difficult problem to go about, right? It's not that it's intractable. People are looking at it in various different ways, but it is significantly harder than, or at least of a significantly different kind of flavor than doing something similar for a classical program or a classical algorithm, right?
Correct. Okay. So this is, see, once again, I mean, I'm going to add some comments. See, that's the way it learns is very much dependent on the input data and the training data. Because if you were to write an algorithm, okay, compared to an algorithm, how would you do? You would try to kind of force your, scheme, or, which is what makes the algorithm. And you will try to do it in somewhat of by understanding what the, how it should behave for different classes, different segments of your input data and so on, which is not exactly how it is done. In that sense, it's a black box.
Yeah.
Once you train it. Yeah.
Right. Yeah. And the other slightly point that I think you touched upon was that you're talking about, this number of layers and this hierarchical structure. So yes, I mean, it is true that one has some kind of an intuition as to, okay, these hierarchical structures should, so these multiple layers should capture some sort of a hierarchical structure, right? But if even that is firstly, it's not always the case that it turns out the neural network is doing that. It might be that the first layer is like, let's say the first three layers are all identifying structures at a similar level of detail, right? So you might have that, you've got one node here that is identifying a line, another node here that is also identifying a line, and so on, right? So usually these things become a little bit more messy in that sense, and harder to interpret from that perspective. But also what can happen is, if I tell you that, okay, this is the neural network and this is sort of, each layer is doing some sort of a hierarchical structure, it's still very hard to know what are those hierarchical structures, right? Like, for example, even if I tell you that, okay, there is some node somewhere which is identifying a line, that does not really help you in any way of identifying which node it is, right? So even though this is a high level intuition, that really does not help us into unpacking and sort of understanding what is it at a sort of granular level or a per neuron level that neural network is doing. It doesn't necessarily allow us. It is definitely some intuition that can help us a lot in that direction, but it doesn't necessarily allow us to understand what's happening at a per neuron level. So does that sort of clarify things a little bit for you? What I mean when I say things are a black box?
Okay, one more question. Yeah. 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 So what is the role of the activation function here? Okay, now this is complicated, so I'll let you ask.
Hello?
Yeah, I can hear you.
Actually, the thing is, for the particular neural network we are talking about, it basically is giving us, for each and every node, it basically is giving us some sort of, like, we are applying some sort of activation function in terms of fuzzy, like in terms of sigmoid. Maybe it is 57% case A and the rest percentage of not being case A, right? Now, this particular slide, start.
Hello. Can you just repeat yourself after 57% case A and not case A?
Haha. Okay. So our target is for each neural network, our target is to classify whether this is a case A or not. I mean, which percentage should we assign to this fact to be case A? That is the thing, right?
Yeah.
When we are talking about the fact that our output or our target is assigning score to each and every digit for a given input,
Mhm.
so it is like we are expecting some sort of result, like some x1 percentage of 0, x2 percentage of 1, and
Right.
x9 percentage, x8 percentage of like till now.
Precisely. Yeah.
Yeah, so are we doing some sort of parallel processing to identify the percentage or the probability for each and every digit for the neural network? Or like one single neural network is giving me all 10 probabilities of being 0 to 9.
Yeah. So the second, it is the second case, right? So when you say parallel processing, of course, one thing that I want to say is that I'm not even going into any of the level of details as to what computations are going to happen parallelly in whatever hardware you're running it on. That is, at least for a current description, that is not really, does not really matter for us. Like, you can code it up in various different ways, and usually things are heavily parallelized over the GPU. But not going into that, it is the case that you would have multiple outputs on the input. So for example, if you look at this diagram, there is sort of two inputs and two outputs, right? So you can imagine that in this digit recognition case, whatever neural network you're going to have, it's going to have some huge input layer corresponding to all of the pixels in the image, and then finally some hidden layers and so on, and then finally you're going to have 10 output layers, right? 10 output nodes. So each one of these 10 output nodes is going to give you the probability of one particular digit. So the first one is going to talk about the probability of this input image being labeled as 0, for example. The second one is going to talk about the probability of each input image being labeled as 1, third one being labeled as 2, and so on.
Okay, all right. So we can configure the whole thing within one particular network, and we can get our desired scores for each digit.
Yes. Yeah. Now, of course, conceptually, there's nothing preventing you from even having 10 separate networks for recognizing these, right? But the idea is that, if you have one network, you can probably share a lot of the hidden layers. Like you are, in fact, sharing a lot of the hidden layers, and that makes sense because the task of identifying the digit 0 and the task of identifying digit 8, it will probably share a lot of the low-level processing. So it makes sense to have one network to do all of that as opposed to having 10 separate networks. Yeah.
To reduce the computation.
Yes, exactly. To reduce the computation size. Yes. Yeah. And so another question that you would ask is, what is the significance of the activation function, which is, I think, a point that I will sort of make right now, which is that this activation function is actually very crucial to this neural network, in the sense that if you do not have a nonlinear activation function, then the entire structure is just a set of linear operations, right? So for example, if your activation function is identity, right, or some other linear function, then what happens is this entire structure essentially just reduces to one affine transformation, right? Because whatever you're doing in this layer is linear. Whatever you're doing, whenever you're taking the inputs from one layer to the outputs of one layer to the inputs of the other layer, that entire operation is just linear, right? Because you're just taking some linear combinations and adding some bias. So if then at each node, whatever you're doing, if that also turns out to be linear, then you just have a composition of a bunch of linear functions, which is itself going to be a linear function, right? So if you don't have some nonlinear activation function, it can be a sigmoid, but there are also other choices, which might get into in later slides. But if you don't have some activation function which is nonlinear, then the entire structure becomes linear, which is going to be like strictly, much less expressive. So it's very hard to imagine that just a linear function would be able to do something like this digit classification, right? So you would need nonlinearity, and these activation functions is where sort of the nonlinearity is being injected. So in some sense, you're doing some linear linear operations, and then you're based on those linear operations, you're going to so you're going to pass the output of that to the activation function to make sure that to introduce some nonlinearity, which is going to make sure that this entire thing does not collapse down to be linear.
Yeah. Well, you can go ahead. And she has one other question, but she will defer until later. Yeah. Please move on.
Okay, sure. Yeah. So at this point, I just want to briefly talk about. So basically, I've got 2 slides briefly talking about one question that was asked some time back, which is that is there always such a function f, right? And I mentioned that it really depends on the class of functions you're looking at. So right now, the class of functions we're looking at are these deep neural networks, right? Which is that this sort of a structure where the theta is the weights and biases and so on, right? So it turns out that for this kind of class of functions, for any given function, in fact, you can approximate it up to any degree that you want, right? And this is sort of called the universal approximation theorems, right? So I'm going to firstly state these theorems in a fairly intuitive way, and then in the next slide, I've got a much more sort of detailed formal description of that, which, for the sake of time, I'm not going to go into too much details of. If you have questions on that, I'd be happy to answer. But at least this is the sort of intuitive description of what this theorem says, right? So this says that if you have a deep neural network where your activation function is some continuously differentiable, and it's not a polynomial, okay? So the theorem the proofs of the theorem depend on the activation function being slightly more complicated than purely a polynomial function, which is the case for most things, right? So this sigmoid, it's actually something that involves exponential terms and so on, right? So these are usually fairly complicated functions, these activation functions, right? So suppose you're given such an activation function, right? And you're only allowed to construct DNNs based on this sigma activation function, right? Now, what does the universal approximation theorem says? it says that given any continuous function f, right? So f is any continuous function on Rn, or let's say some compact subspace of Rn, but basically some bounded part of Rn, right? And you're given any epsilon, which is going to be the degree to which you're looking for, like degree to which you're looking to approximate f. It says, this theorem says that there will always be a DNN n. There's always going to be two kinds of ways of constructing a DNN that actually approximates your f up to epsilon, right? There's one DNN n with one layer, but one arbitrarily large layer, right? So this DNN n can have a very large layer, but it's always going to have one single layer. So that, of course, this sort of an this DNN is actually epsilon close to f always, right? Similarly, there is going to always be so another DNN n where you can bound the size of each layer, but you can have arbitrarily many layers, right? So this DNN is, suppose in some sense, has got a bounded width but arbitrary depth, right? And the other one you had bounded depth but arbitrary width. And in both of those cases, you can sort of have DNNs which arbitrarily closely approximate our function f, right? So basically what these theorems tell us is that no matter how complicated your function is, you can always choose a DNN that has got either one layer which is wide enough, or only bounded layers, but enough number of such layers, so that no matter what your function is, how complicated it is, your DNN can actually approximate it up to whatever degree of approximation epsilon you set, right? So if you give me even if you give me a really complicated function, and even if you ask me to approximate it very closely, I can do that. The only thing is that I'll have to probably have a fairly large DNN for doing it, but nonetheless, I can do that, right? So these are the sort of universal approximation theorems. And this is the sort of the full sort of theoretical, full statement of these theorems. And there are bounds involved. They actually provide certain bounds on the sizes of the networks and so on, right? So I'm not going to get into all of those just for the sake of time, but you can look into this. And then people have done several sort of refined versions of these theorems and so on.
Yeah, Diganta, I have one question here.
Yeah.
Now, this universal approximation theorem applies regardless of what kind of activation function you choose?
Yes. So the only condition on the activation function is that it should be so this basically these are the conditions of the activation function. It should be continuous. It should be continuously differentiable almost everywhere, and it should not be a polynomial.
Oh, sorry, I missed that line. Okay, yeah, you already have it covered. Yeah. Okay. Any questions?
So any other questions?
So what does, I know that you didn't want to dwell too much on your next slide.
Mm-hmm.
What do those two theorems really tell? I mean, if you want to summarize.
Oh yeah, that is what I've said over here. So the first theorem is basically talks about this case where you have got only one layer, but it is allowed to be arbitrarily large. And the second theorem is dealing with the case here where there is multiple, there are only layers of bounded size, but there can be arbitrarily many such layers. So these are the sort of the questions, the theorems.
Okay, so those theorems are more technical.
Yeah, and these don't have too much extra detail. So initially, I just had a slide with these two theorems, but then I thought that I'll just instead just give a brief summary.
Okay, go ahead.
Yeah, the only extra details in this are the precise statements. What is the bound? What is the domain of the function? The domain has to be some compact domain and so on. So there's some more technical details that is present, but not too much. So any questions?
Yeah, there's one question here.
Yeah.
In the second theorem, you haven't mentioned that sigma is a non-polynomial activation function.
Sorry?
In the second theorem, we haven't mentioned that sigma is a non-polynomial activation function. It's just in the
Okay. Yeah. So this also I should probably miss this here. So actually, if it is even if it is polynomial, what it turns out is that the entire thing collapses to be a polynomial, which is for which there are already approximation theorems. So these bounds don't hold. It's not that you don't have an approximation theorem in the polynomial case. It is just that these specific bounds don't hold, and you can say a lot more things in the polynomial. Like you can say different set of things in the polynomial cases, right? Okay, I'm unfortunately unable to write with a mouse right now, but yeah, there is the non-polynomial condition over here as well.
Hello?
So is this okay?
Yeah, just I have just a query.
Mhm.
Will you suggest some resource from which we can have a look at the proof of this theorem, like the justifications?
Yeah, I'll send those over. Yeah.
I think maybe, Diganta,
Mhm.
you could include in the slide itself some references. If you
Yeah. Okay. Yeah. Sure. Yeah.
And at this time, I also want to mention, I mean, I have not uploaded any references, okay, textbooks and so on. There'll be some that I will do, whether those reference textbooks that I will be uploading, whether they go into this particular approximation theorem, I don't know. They are written more in terms of from the point of view of verification, so they may gloss over the actual basis, for DNN, how they work. But nonetheless, that's a good point, and I'll try to do that. Yeah, thank you.
Yeah. So I'll definitely add references for the proofs of these, and yeah, either upload them to Moodle or include them in the slides.
That'll be good.
Yeah.
Move on.
Right. Yeah. So there's another sort of theoretical way of looking at another property of this class of functions is this neural network that I want to talk about, which is from a complexity point of view, which is that if you think about even for polynomials, you have these universal approximation results, right? Like you might have seen it before that if I give you any function, continuous function, which is no matter how much complicated, and I give you some epsilon, you can always find a polynomial that has got sufficiently high degree that actually approximates this function up to epsilon, right? So it's not that these universal approximation theorems are really anything new or anything special about neural networks, right? So even polynomials have universal approximation, for example, right? But really, what is a bit more interesting about neural networks is that it's not just that they're universal, they have universal approximation, but it is also the case that they are much more compact in some sense, right? And one way to sort of look at this compactness is that it can sort of capture functions with exponential amounts of detail, right? So this is an intuitive view. There is a sort of so there is something that can be interpreted as a consequence of this, which will come to, I think, in later slides, or maybe in a later lecture as well, which is that these uh, 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 neural networks are sort of, in some sense, polynomially expressive, right? So let's consider a special kinds of DNNs, which are DNNs with this particular activation function, ReLU. So this ReLU activation function is just defined as being 0 if the input is less than 0, and defined as being X or identity if the input is greater than 0, right? So if the input is less than 0, we just say 0, and if the input is greater than equal to 0, we just set it to identity, right? And in this kind of a special case of DNNs, it is actually very easy to see that these DNNs will be, as functions, these are going to just be piecewise linear, right? So firstly, is this clear to everyone that this will be piecewise linear? Because each node, if you think about it, it is just a linear function with sort of two pieces to it, right? So it's piecewise linear with two pieces, and then you're just composing these functions over and over again, right? So each linear piece, as long as you within the linear piece, no matter what composition you do, you're going to be linear itself, right? So the only non-linearity that is coming are in these points where you're going from this situation where you're setting your output to 0 to you're setting your output to identity, right? So you're only going to have non-linearity in these places, and everywhere else you're going to have linearity. So what you end up with is piecewise linearity, right? And as a graph, this sort of looks something like this: 0 up until here, and then identity. Yeah. So any questions regarding why, or is it clear to everyone that why this is, if I set ReLU as my activation function, why this neural network is going to be piecewise linear?
Yes, sir, you mentioned that even polynomials can be good, like universal approximators, but you said that DNNs are compact in some sense, more compact.
Yes,
What
yes,
do you
yes.
mean by that?
Yeah, so I was coming to that. So I was coming to that, and I was just going to use this ReLU DNNs as a special case because it's slightly maybe easier to see in that for these ReLU DNNs, right? So I'm going to come to that point. So just before coming into that point, I'm just saying that this is going to be piecewise linear. So I'll just is it clear that if I use ReLU as activation functions, DNNs are going to be piecewise linear?
Yeah, I guess that's.
Yeah, okay, sure. So in that case, then I come to this question that you're asking, which is that what do we mean by they're going to be more compact, right? So let's say that we have some DNN, right? And we add a neuron, right? So when we add a neuron, I can ask a question of how many new such pieces am I actually introducing, right? So if you imagine what would happen when we add a neuron, what is the sort of worst case scenario that is going to happen if we add a neuron, right? So previously my neural network is itself a piecewise linear neural network, right? Now, when we are adding a neuron, it is possible that for each linear piece in the piecewise linear neural network, this particular new neuron can see both negative and positive values within this piece, right? So in that scenario, the value of this neuron is going to be both negative and positive for each piece on my original neural network, right? So in the negative cases, this new neuron is going to be set to value 0, and in the positive case, it's going to set to value x. So whenever we are making this transition, we are going to end up getting a split in the piece, right? So then what happens is that each piece in some sense is going to split into two, resulting in the doubling of the number of pieces, right? Of course, this is the worst case scenario. It might happen that for a particular neural network, if you add a neuron in some particular way, you can get away with without having this doubling, right? But intuitively, in the worst case scenario, if I'm adding one neuron, it can definitely be the case that no matter what piece I look at, which is whatever linear piece I look at, that particular neuron is still going to shift from this negative domain into this positive domain, which means that once I've added the neuron in this new network, whatever my original piece was is now going to actually be two new pieces, right? There's some nonlinearity or some break being introduced or some split being introduced in that piece as well, right? So in the worst case scenario, adding a neuron is going to grow the number of pieces that I have in this piecewise linear function exponentially.
Yeah, I think there's a little bit of doubt here as to what you mean by you split into two. Am I right? Is that the thing? So, yeah, meaning doubling the number of pieces. I mean, you will. Yeah, can you elaborate on that? So you say you split in the sense that the network is split.
No, so what I mean is
what the as you dynamically compute the function. Is that what you mean? Yeah. What do you mean by splitting?
Yeah. So
maybe an example.
Yeah, sure. So let's suppose that that this is sort of the, so let's say that we have a neural network which has got two inputs, right? And let's say that it is a piecewise linear function, right? So let's say that the function actually has got 4 linear pieces right now, which looks like this, right? So within this region, things are linear, within this region, things are linear, within this region, things are linear, and in this region, things are linear, right? But it's just that in these these lines, we have some amount of nonlinearity, right? So it's piecewise linear function where everything is linear within each one of these four regions. But overall, the function is nonlinear because if you move from one region to another, you're going to get some nonlinearity, right? So you can imagine this is sort of looking like a folded piece of paper where the folds are along these two lines, right? So this is what I mean when I say that this ReLU-DNNs is going to be sort of piecewise linear, right? Now, what if this is, suppose, let's say this is the picture for one ReLU-DNN, right? Now, if we were to add another neuron, right? So let's say this is the ReLU-DNN with some neurons, right? So it's some ReLU-DNN that looks like this. I've got an input and I've got some hidden layer and I've got an output, right? So now I'm adding another neuron in this hidden layer, right? So now if I look at sort of what the value of this neuron will be, right? It can be that in this piece, this neuron can have both positive and negative values, right? So in this piece, there will be another line along which, below which the neuron has got a negative value and above which it has got a positive value, right? So if I look at this piece, the contribution from this neuron, now that I've added this neuron to the network, the contribution from this neuron is going to be 0 below this line, and whatever the input to this neuron is above this line, right? So this neuron is again going to result in another sort of crease or fold or split appearing, right? So this piece is now going to this entire piece is now going to not remain linear, because as you move from the region in which this neuron is seeing input less than equal to 0 to input greater than equal to 0, the contribution from this neuron is going to change non-linearly, which means this piece as a whole is not going to any longer remain linear, right?
Yeah,
Instead, what you're going to get,
what you're saying is the the complexity of the piecewise non-linearity of the function that it computes can be as complex as possible, right?
Yes, and that is in fact an exponential amount of complexity is going to be there, right?
There's exponential complexity in terms of the this
yes,
the behavior of the function that it computes.
Right.
Okay,
So this is what I'm saying, and what I'm saying is that in the worst case scenario, it may happen that this sort of a split appears in each piece just by adding one neuron. So in each piece, sort of, there's one region where the neuron is 0, non-zero, 0, non-zero, right? So each one of these pieces ends up splitting into 2, and you end up getting, previously we had 4 pieces, now we've got 8 pieces, right? So I'm saying that this is sort of what can happen in the worst case scenario.
Okay.
And so if you imagine, if I have a neural network with n neurons, it can sort of represent a function which has got this 2 to the power n linear number of pieces, right? And which means that if I want to represent a very complicated function, which might need 2 to the power n number of linear number of pieces to represent or to approximate efficiently, I would only need n neurons to do it, right? So this is the sort of intuition that I'm going to go for, and I'm going to come back to this and state this in a bit more formally, or relate this to a much more formal statement regarding NP hardness of certain problems when looking at, or certain analysis problems or verification problem for neural network, right? And so there, this intuition will become a bit more clear. But I think that may not happen at least in this slide deck, but like sometime later on, I'm going to talk a little bit about the hardness of the verification problem for neural networks. And there I'm going to come back to this idea of the complexity or the number of pieces and the relevant complexity and so on.
Yeah, so I guess the point is that, this thing in this particular slide that it is denoting is that the kind of functions that DNNs compute are quite complex in terms of the number of things, and and because DNNs have these layered structures, that they are a compact representation of this complex function, correct?
Yes. Yeah.
Okay, good. Please move on. Yeah.
So
okay. 515. Okay. because we started a little bit late. I guess it's okay, you know, for you guys.
Okay.
5:15, yeah.
Okay, so 5:15. Okay, sure. Thanks. Yeah, so this is what I wanted to say about neural networks as function approximators. So now I'm just going to give
We will okay.
Yeah.
From a logistics point of view, you know, because I want to cover, you know, that's why I've split. Normally, I would have let Diganta continue and talk about this optimization and all that gradient descent question and so on. But because I also wanted to cover the logic recap before the course registration deadline, and then give you an opportunity to test yourself as to the extent of logic background that you know, need to continue to help you to decide to continue the course or not. Therefore, I'm going to be splitting Diganta's thing. Therefore, details of gradient descent, etc., will probably be covered in the fourth lecture. Okay, and that's how we plan it. Yeah. Go ahead. Go ahead, Diganta.
Yeah. So in the remaining 15 minutes, what I'll do is I'll just talk very briefly about what does it do we mean when we are saying that the training process and so on, right? So there is some details which I'll not really get into, right? So I'll instead give a sort of a higher level view, and yeah, so and then that is it. Then we can move on to sort of the yeah, so then in the next lectures we'll go into the more details of the gradient descent and so on, right? Yeah. So so far we have looked at what these neural networks are as this parametrist function approximators, this F in our sort of picture previously, right? So this F, but we have not really talked about how to find theta, right? And that is where all this gradient descent and all of that will come in. And I'm not going into too much details of that, but just give you the overview and what the framework will sort of look like, right? So how do we find theta, right? So the idea is that we have a bunch of data, right? And this theta we can sort of find as expressing this. We can sort of express this finding theta as an optimization problem based on all of the data that we have, right? So what we will do is we will define something that we call a loss function. And this loss function is going to be based on some statistical principles. And it's also going to be based on the data, the examples that we have, right? So for example, the loss function can be for each input X, right? We can look at, so if we expect the output to be Y, we can define the loss function as something like this. We can say that, okay, look, take N, pass this X for a given theta, you know, N will give us some value for each input X, right? And then we look at the sort of distance of this from the expected value, right? And we can then square and take a sum, right? So this can be sum over all of the X, and then these Xi's and Y's are basically our examples of data, right? So notice that this as a function, it actually does not depend on this Xi's and Y's. The Xi's and Y's is some fixed list, right? So this is just a function of theta. So we can then define our L theta as just being some function like this, right? And this in essence captures how much error we have on average, right? So here I've been talking about distance, but then of course the distance you can ask in what metric, and we can define various different kinds of distance and so on, right? But this is one example of what this loss function can be, right? So this loss function for a particular theta, it's going to sort of use this theta to evaluate, or use this theta to set up N, and then evaluate N on a bunch of test examples. And then it's going to come up with some measure of how good we are doing on these test examples, right? So in this case, it's going to come up with the average distance, or the average distance from the expected results that we're seeing right now, right? So then to find theta, one way of doing it, or the way that we do it in machine learning, is that we find theta by optimizing this theta so that we minimize this loss function L, right? So this is the sort of general idea behind machine learning. And depending upon the kind of data and the way we are constructing loss functions, we have multiple sort of flavors of machine learning. We have supervised learning, which is so far all our examples fit into supervised learning, right? Where we have data has both input and output pairs, right? And then we have unsupervised learning, where the data has got only input pairs, and we're interested in things like so the loss is then not just the distance from the expected value, but it's more things like how closely are we separating two kinds of data and so on, right? So for example, if I have a bunch of English text, I can define my output as being some vector on which I want to measure the similarity between words in the English text. And then I can define some sort of statistical measures as to how closely we are actually achieving that with respect to the English text that we have. And based on that, we can come up with the loss functions, right? And there are other paradigms like reinforcement learning and so on, where it is, it is not directly a loss function that we are going to optimize, but rather a reward function based on runs of a game that we are going to optimize. But this is the sort of high level view of what we tend to do when we set up gradient descent in machine learning and so on, right? And then I've got this example, which I think I'll not go into for the sake of time. But instead, I'm going to give you this more sort of high level view. I'll go into the details of all of these examples later on. So yeah. Which is this high level view is that, okay, fine. So now that we've realized that we need to optimize L, how do we optimize L, right? So the particular algorithm that people generally prefer, which tends to work really well in practice, is called this gradient descent algorithm, right? So if you can imagine this loss function L can be thought of as this complicated surface. So theta is usually some very high dimension, like it's got as many dimensions in it as you have weights and biases and so on, which is in general going to be quadratic in the size of your neural network, right? But your loss function in general is going to be some surface on top of this theta, right? And we're trying to find a minimum of this loss function, right? So the way in which gradient descent is going to do is it's going to start at some point, and then it is going to calculate the gradient of this loss function. So remember that so far in everything that we have been constructing, everything has been differentiable, or at least differentiable almost everywhere, right? So it actually makes sense to say that we'll calculate the gradient. The gradient is going to be well defined, and we can calculate the gradient, right? So at each point, it's going to calculate the gradient, and it's going to move a small step in a direction opposite to the gradient, right? And then it's going to calculate the gradient again and move again in a small step, and it's going to repeat that, and ultimately it's going to approach this sort of minimum, right? So this is the gradient descent algorithm. But so I just want to present this algorithm at a very high intuitive level. And I want to make a very small point about this algorithm, which is that in general, of course, this algorithm can only give you, so this algorithm is going to get you to the, is going to approach this local minima in a case where your loss function is convex. But in generally, the loss function is not going to be convex. It's going to usually be much, much more complicated than that, which means that in general, this algorithm, the only guarantee of this algorithm is that it's going to get you to some local minima, right? So you don't really know whether you can get to a global minimum, right? So there is no guarantee about this algorithm giving you global minimas, right? Which means that, in general, there might be a really nice neural network out there, which is globally the best possible neural network. But in general, gradient descent might not necessarily be able to find that particular neural network for you. What it will find is some neural network that is still better than, maybe other closed neural networks in a local neighborhood, but it may not necessarily be the globally best possible neural network, right? But of course, this does seem to work very well in practice, and that is in no small part due to a lot of engineering and a lot of heuristics And a lot of details that has gone into things like, for example, as the question was asking, deciding intelligently what the starting values of theta should be, right? So a lot of this effort has gone into this gradient descent algorithm and making it work for the neural network case. And due to that, and some other reasons which are not as well understood, this seems to work very, very well in practice. So all of these headline results that you see about ChatGPT and so on are fundamentally a result of somehow gradient descent working and scaling really, really well to really, really large neural networks. Yeah, so I've got some details on how to calculate gradient descent, but I think this is a point where I would stop. I mean, I was thinking of going into the details of verification, but let's do it on on the next lecture, or do you think I should continue right now?
No, I think we should, as we planned, we should definitely go into gradient descent details, technical details, next time. But what do you have? I mean, you said you want to go into some verification. What do you have? I mean, in 10 minutes for you?
Yeah, I have some slides. I can go into the sort of the brief overview of the slides on verification details. So I think I've got less than 10 minutes. I've got only 5 or 6. Yeah, sure. Okay.
You could just do as much as you can, and maybe that will lead, nicely into, if you had some verification related things, that can lead nicely into my logic lectures. Yeah. Hello. Oh goodness. Hello, are you there? Maybe God said that maybe he is. It said 1 hour 30 minutes. They usually go end the lecture.
Hello, can you hear me?
You're back. Okay. Yeah, I was afraid that they cut you off. Okay, go ahead.
Yeah, sure.
Yeah, I was saying just, I don't mind you spending, a few things about whatever you have on verification, as it will lead nicely into my logic lecture.
Yeah. Okay, sure. So, yeah, let's go to that. Yeah. So the basic thing that I want to talk about with respect to verification is I want to sort of motivate it from at a high level point of view why we would want to do verification, and then also just introduce this verification problem, the formal definition of the verification problem, right? So then that sir can then build upon from in his logic lectures a little bit more as to what these terms mean and so on. Okay.
Perfect.
Yeah. So far we have seen these neural networks, right? So one of the things that I would want to point out that when we are looking at these neural networks so far is that you would have noticed that in all our language, whenever we were talking about this network, we're only really talking about whenever we're saying that we're going to learn the network and so on, we're only really interested in the behavior of the network up to some level of approximations, right? So this gradient descent is only really going to, so this gradient descent algorithm as I described to you, right? It's only going to give us the local optimum. Even then, it's not really going to give us this precise local optimum point, but it's just going to get us closer and closer to it, right? So in practice, whenever we're training DNNs, what we end up getting is some approximate behavior. And that is inherent to the sort of formalism that we're operating in within machine learning, right? We're only interested in the average error. So we're only minimizing the average error. So at any given point, we're only going to get a DNN that is going to be in some sense, some approximation of whatever the best thing is, right? But this is basically an issue because this also means that DNNs are going to be inherently error prone, right? So on one hand, this framework allows us immense generality, right? You can just, you can take this gradient descent framework and do it for images of cats. You can do it for words. You can do it for emails when you want to detect spam. And the same sort of framework basically works in all of those cases, right? Which is fairly unprecedented, but in the large scale of things. But it is also inherently error prone because it is inherently approximate, right? So for example, one source of errors is that you can generate adversarial attacks, right? So I was talking about detecting cats. Let's talk about a much more sort of real world relevant example, which is, say, detecting things like stop signs and traffic signals in a self-driving car, right? So even if you have a self-driving car with a camera, you want to sort of take the images coming out of that camera and you want to detect, okay, look, there's a stop sign there, and the car should slow down and finally stop, right? But you guys, you can imagine, if we are only if this is inherently approximate, and if this is inherently going to give us a network where things,
I think I have motivated. You can kind of go to the next slide. So I have
yeah.
motivated this thing in my introductory lecture.
Okay, sure. So I'll move on. But yeah, so basically the idea is that this there's a lot of error that can be involved, right? So then what we would like to do to eliminate these errors is that we would like to solve this problem, which we call the DNN verification problem, right? So what is this problem, or what is the problem formally, right? So we're given a DNN, and with respect to this DNN, we'll be given some precondition and some postcondition, right? So for example, the precondition in this traffic signal example, it could be that, okay, whatever input image I have, it is the image, it has got some epsilon perturbation added to the image of an actual traffic signal, right? So the camera might have some inherent amount of noise, and we're saying that, okay, look, whatever input image that I have is going to be the image of a stop sign plus some amount of noise, right? And then the post condition is going to be some property of the output. So the precondition is a property of the input, and the post condition is a property of the output. So in this case, the post condition, for example, could be that the output of the network definitely says that it's going to be a stop sign, right? So for all of the probabilities of the various kinds of signs that the network can identify, the probability of the stop sign is the highest. So the car actually decides to stop, right? So given this sort of a thing, what we sort of want to verify is that given that the input satisfies the precondition, we want to make sure that the output of the neural network always satisfies the post condition, right? So formally, we can write that as like this, where we're saying that we have some input which satisfies this precondition. So that is, for example, some noisy image of a stop sign, and we have an output coming out of the neural network, right? So there is some set of probabilities assigned to, the image being a stop sign, the image being a go, image being 50 kilometer per hour speed limit, whatever, right? And given this situation, we want to always make sure that in the output, the probability of the stop sign is the highest. So that is the post condition of the output, right? So here, these two things, this phi and psi, right? To be able to sort of write this formally and then argue about this formula and finally develop algorithms to do this, we have to encode these things mathematically, or as leading into what Sir is going to talk about in the next lecture, in this sort of language of logic, right? So we would want to sort of encode phi and psi mathematically and logically in general. So for example, if you have a situation where you're looking at some collision detection sort of a scenario, this can say that the value of the left sensor is greater than 9, right? So this is a very precise logical statement. And similarly, the score of the left turn is less than some particular value is another precise logical statement that can be a part of this, right? So in general, these phis and psis tend to be very precise, concrete, logical statements about our inputs and outputs. And then the DNN verification problem is to develop algorithms that will automatically check whether or not this kind of a logical statement holds, whether or not this implication holds. And if it does hold, it's going to produce a proof. And if it does not hold, it's going to produce an actual counterexample, right? So this is the problem. So, do you think that this is a good point to stop?
Yes, I think so. I think one point that I want to emphasize is that then X and Y's are universally quantified in the sense The problem is one of showing that for all x's that satisfy phi x, the y, whatever y that n produces for that x, yes,
Yeah.
satisfies psi. So in that sense, the verification problem is a logical problem, like the one that I showed in the last class about the program verification of proving equivalence of two things. So the challenge lies, because you could do testing. You could just test unit test data of a finite number of tests. You can just run your network and then test it. But here, what we're trying to do is that this thing never gets violated ever for any kinds of test inputs in your that satisfy your input conditions. And that's why these algorithms are hard to check this. Okay?
Yeah.
And, at least NP hard.
Yeah.
Algorithms and,
Yeah.
okay, I think this is a good point to stop and take some questions, just quick questions, or you can reserve it for next time also. Any questions? Thank you. I don't know if Madhukar is still there. Madhukar?
Yeah, yes, sir, I'm here.
Okay, okay. I just wanted to let you say hi to the class. Madhukar is joining us from Delhi, so he will be the other guest lecturer that you'll be hearing from as well.
Yeah.
Yeah. Okay. So, any questions?
Isn't okay? I don't think I know enough of the problem to be able to formulate a question, but doesn't the problem seem to be more of being able to formulate a, like, for example, if you consider the cat question, or in general even for a stop sign, if it's an image classification question,
Right.
then the bigger issue of being able to translate these like slightly variable sort of bit data into some actually mathematically encodable precondition, like
Yes. Yeah.
more than actually getting into a precondition postcondition.
Yeah. Yeah. So you're saying that the problem is more of getting this phi and chi, and rather than verifying, right? I, yeah. So if that is the question, yes, it
That's
is.
also right.
Yeah.
I think verification has, I mean, I'll add my 2 cents
Yeah.
worth and can answer. Yes, verification has this modeling issue. How do you make these, come up with these specifications that you want to verify and encode them in the logic of your choice? And then you're right that it is not it is challenging, okay, to encode. But once you encode, how exactly will you verify? You know, that's also a challenge, and that is because of the complexity. How exactly will you manage? You know, and when you apply it to real networks that can have you know, millions of nodes. I mean, at least if not millions, hundreds of thousands of nodes, neurons, and so on. That's my 2 cents worth. I mean, you go ahead, Diganta, your perspective. Yeah.
Oh, yeah, sure. So I agree completely with sir. Is that it is the case that, you know, so I agree with what you're saying as well, which is that it is the case that coming up with this phi is itself a non-trivial thing, and that has classically always been the case, as sir was pointing out, with verification, right? But I just want to say 2 points, which is that, you know, in general we have this spectrum, right? So on one end of the spectrum, we can say that, okay, we're going to use all of this. So let's talk about the stop sign example, right? We're going to use the stop sign data, and we have some 99.9% accuracy, and we're just happy with that, right? So we've done a bunch of testing. The testing has given us some results, and we're happy with the results from the testing, right? And then the other end of the spectrum would be to actually come up with an actual deterministic algorithm that we understand every bit of detail of, and therefore we can sort of verify completely that it will always correctly classify a stop sign and never misclassify a stop sign, right? But really, you know, each end of the spectrum has got its own issue. This end is completely infeasible in practice, or at least so far it seems like it's infeasible in practice, right? And this end of the spectrum, it seems that you know, it is really not good enough, because even though there have been really sophisticated networks achieving really great accuracy, it has been shown that these can be fooled by very simple sort of perturbations, which are perturbations to the image that can appear in real life. For example, a piece of tape covering a bit of the stop sign, not even the letters, just some corner of the stop sign, right? But see, these kinds of perturbations, on the other hand, can be captured by some middle ground. So you can say that, okay, I'm going to start with some image that I know is definitely a stop sign, and then I'm going to add some amount of noise to it, or I'm going to modify the image in some way. I'm going to add a black box at some point in the image, right? So you can then sort of encode these kinds of perturbed versions of the images as your precondition, right? And then do a verification on that. And that basically lands you somewhere on in the middle of the spectrum, where you have more confidence on the DNN than just purely doing some testing. But of course, you don't have enough confidence on your system as if you would have done something like a full-fledged analysis, right? So this is one point that I want to make. The other point is that oftentimes these neural networks, the really safety critical situations in which these neural networks are deployed are larger, are parts of a larger system. So again, coming to this sort of self-driving car example, the self-driving car is more than just the neural network, right? If you know, the neural network is really a part of a larger system where the image is coming into the camera, and then the neural network is giving some decision, and based on the decision, the car is making some movement, and then again, based on the movement, it's now in a different position of the world, which gives us a different image, and that new image now comes with the camera, and so on, right? So these are the sort of closed loop systems, we call them, in which these neural networks are usually deployed, right? And there it's actually much more easier for you to be able to say what you mean that this entire system is safe. For example, for a self-driving car, the entire system is safe as long as this car itself doesn't collide someone, right? And there has been a lot of work which basically takes these more complicated systems where neural networks is just a part. Even before neural network came into this picture, there has been a lot of work where you have a complicated system, and they reduce the problem of verifying safety for this entire system into multiple queries of this particular form. And we'll see at least a few papers where similar thing has been done for neural networks, or systems involving neural networks, I should say. Um, so there, in some sense, you know, the entire problem of, you know, given a self-driving car based on a neural network analyzing the input from a camera, given this system, the problem of checking whether it is going to collide with a tree has been reduced to, or can be reduced to, a problem of, okay, let's isolate out the neural network, given inputs of these particular kinds, satisfying these particular logical um, or you know, these particular mathematical conditions, is it always the case that the output is going to satisfy such and such mathematical conditions, right? So that kind of a analysis has been done, and of course, even in those cases, you can make the same argument. Okay, look, you know, is it really the case that the self-driving car is not going to collide a tree in all possible situations, or are we looking at some subset of situations, and so on? So in general, the question that you'd avoid asking is a very fundamental question that is in general hard to avoid. But anything is going to give us more confidence. And definitely another way of looking at this verification problem is that it is something that comes up as a part of solving things that can feel, at least for the case of neural networks, much more concretely definable. For example, from the self-driving car example, right? So does that, yeah, so that was just my perspective on this.
I think so. I think that the closed loop verification was a good example of how you could decompose. And I'm sure that, you know, I want to, just end adjourn at this point. And, you know, these questions we'll be looking at, you know, more when we study some of the papers, you know, the thing. And then maybe with some examples after, you know, after the introduction to programming logic, etc. You know, one of the exercises that we'll be doing is taking some simple neural networks and then proving some of these kinds of things using the tool. So you will get exposed to understanding what exactly it means, and then maybe even getting you know, those examples that shed light on the kind of questions that you've asked. Yeah, thank you. I mean, so thank you for your patience. We ran out of beyond 10 minutes. Yeah, so I see you. You know, please don't forget to fill out the forms and submit them. Okay, and do that. Thank you. Yeah.
Thank you.
Nikita. So I'm going to
Thanks a lot. Yeah.
yeah, end the lecture.